This is a lesson on radical numbers and exponents and fractional exponents and simplifying radicals. So a couple of definitions to start off so we can so you can know the terminology that I'm going to be using. One is the root of a number. The root of a number is when a number, I call A, is multiplied by itself a certain number of times, n, that gives another number, right? So in this case, a to the nth power is equal to b. That means that a is called the nth root of b because a to the nth power is equal to b. The most common root that we will talk about is something called the square root, which means that n, the number of times this number is being multiplied by itself, when that number is equal to 2, that's called a square root, right? So let's use some different letters here. Our number d multiplied by itself 2 times gives a number f. That means d to the second power is equal to f. That means d is the square root of f. For example, 5 to the second power is equal to 25. That means 5 is the square root of 25. Now, when you see a radical, you're going to see this symbol here, it's a hook with a horizontal line up top. There's some components here that I want to mention, right? There's a radicand, which is the term referring to whatever's inside the radical, not just one single value, but anything inside of a radical is called a radicand. This particular radicand is made up of a base x to an exponent b, and something here that you rarely see is called an index, and this indicates the root of this radical. Right, so the reason why you usually don't see something is because you usually see it like this, which is a square root, right? A square root symbol, a radical symbol, usually, most of the time is given something like this. This is the square root of x. Now, just like denominators of 1, exponents of 1, coefficients of 1 usually don't have to be written down, right? The same thing holds true for an index. An index usually is not written down because that index is equal to 2. So that's the default value. The default value of an index is 2, and if an index is indeed equal to 2, then it does not have to be written down. It is assumed that it's equal to 2, but it does not have to be, right? It does not have to be. You can have what's called a cube root, which means that what multiplied by itself 3 times is going to equal 64, and that's equal to 4. So 4 is the cube root of 64. 10 is the square root of 100. Once you get to the higher numbers, such as the fourth root, let's say the fourth root of 16, that's equal to 2, because 2 times 2 times 2 times 2 multiplied by itself 4 times is going to equal 16. All right, so 2 is called the fourth root of 16. We're going to be working mostly with square roots in this class. And again, a square root is a number when multiplied by itself gives the value of another number called the radicand, right? Here, b is the radicand. So if a squared is equal to b, then a is the square root of b. We covered that already. Now what I have written down here is very common square roots that will be very useful for this unit. Starting from 0, right? 0 is a perfect square because 0 times 0 is equal to 0. 1 is a perfect square because 1 times 1 is equal to 1. And then we get into the real ones. Radical 4 is equal to 2. Radical 9 equal to 3. Radical 121 is equal to 11 because, again, 11 times 11 is equal to 121. and all the way up to 14, right? 225, radical 225 is equal to 15. One of the most important things, we will venture into this in a little bit, because of the nature of a square root, if you are multiplying 4 times 4, that equals 16, which means that the square root of 16 is equal to 4. If you are multiplying -4 times -4, that is also equal to positive 16. Now this symbol signifies what's called the principal square root, which means positive, right? There are different scenarios in which we will have to consider both positive and -4, but that's for equations, not for square roots on their own. But another important thing here is that no matter what's the square root is, right? No matter what this radical is, it has to be positive. It can never be negative, unless we are talking about complex numbers and imaginary numbers, in which we haven't covered yet. So for this unit, it is going to be not possible to have a negative inside of a square root symbol. All right, so anytime this is encountered, the answer will be undefined. So let's evaluate some radicals here. Let's start with this one over here. The square root of 64 is equal to 8. Now, if there's a negative sign in front, that means the square root is equal to -8, right? That negative kind of just carries down, and you take the square root of 64. And like I said over here, if there's a negative inside of here, inside of a square root, then that answer is undefined. Let's take a look here at a cube root. The cube root of 125 is equal to 5, again, because 5 times 5 times 5 is equal to 125. And just like the negative outside of here, the negative can carry through to the answer to sit in front. Now, what about this one here? We have a negative inside of a radical. Does that mean undefined? What I said was a negative inside of a square root is undefined. All right, if we take a look at, let's write it up here. -5 times -5 times -5. All right, if we only do these two, that's -5 times -5, which is equal to a positive 25. Multiply that times another -5, which is that one right there. And this is equal to a -125. So the cube root of -125 is possible to calculate and is equal to -5. Now the reasoning for that is that you can't always say undefined if you see a negative inside of a radical. It depends on what that index is, right? This here, again, because it's not written down, this is an index of 2. But over here, this index is written down. This is an index of 3. If this index is an odd number, then it is possible to have negatives inside here, right? It is possible for the radicand to be negative if the index is an odd number. If it's an even number, then a negative is not possible. Fractions work pretty similarly to just regular numbers, right? A fraction inside of a radical means just the numerator and denominator have separate radicals there. So 2 over 3. We could take the square root of each number individually, numerator and denominator. The square root of a decimal number, you can use a calculator for this, but they work just like regular numbers. Whatever times itself multiplies to a 0.49. That's going to be 0.7 in this case. And just like a square root, a fifth root can be calculated by separating a numerator and denominator. Remember, 1 times itself however many times is equal to 1. So the fifth root of 1 is equal to 1. And for 32, that fifth root is equal to 2. Negative values can be, again, split up the same way. That's negative 5 over 2 for the cube root. And again, over here, it looks like undefined, but again, take a look at the index. Since the index is an odd number, then it is possible to take the root of that negative value. But if the index is even, any negative radicand is going to become undefined. So what about variables? Can you take the square root of a variable, like the square root of x or something like that? The answer is yes, right? And it's all about the exponents in this case, right? When you're looking at the square root of a variable, it's all about the exponents. Basically, an even numbered exponent is considered to be a perfect square. Remember that the rules of exponents are different than the rules of base numbers. So then when you are taking square roots of exponents, those rules are going to be different than base numbers as well. Take the square root of an exponent by dividing that exponent by 2. That's it. So a list of some perfect squares as far as variables are concerned: x to the second, x to the fourth, x to the 10th, x to the 20th, x to the 42nd, x to the 98th. The common theme here is that they are all even numbers, right? But notice that 2 and 10 and 20 are not perfect squares as base numbers, but they are perfect squares as exponent values. Numbers like 4, 16, 36, 100, these are 64. These are perfect squares, whether as base numbers or as even as exponents. But the confusing thing is that most often we are looking at the square root of 100 as 10, but it is different as an exponent. Remember, the rules are different as exponents than base values. So anytime an exponent is an odd number, it's not a perfect square. And we'll go over in a little bit how to handle those. But let's look at the even ones for now. Once again, the square root of x to the 10th is x to the 5th, because all you're doing is taking 10 divided by 2. The square root of x to the 16th, right? The most common answer is x to the 4th, but remember, this is an exponent value, so this is incorrect. The correct answer here is going to be x to the 8th power, because that's 16 divided by 2. It's important to be able to parse out or separate our exponents and base numbers because the rules are different. Take 30 divided by 2, and you get x to the 15th power as the square root of x to the 30th. Right? That's all there is to it. So one thing that I kind of glossed over here is technically the root of a variable has to be written in absolute values. So as long as you are taking an even index, usually the square root, which means it's even, that means that your answer that comes out has to be a positive value. It has to be a positive number. And then in order to ensure that, you have to put the absolute value bars around your answer here, because once again, because we are taking the root of an even numbered index. So watch for that on WebWork, because on WebWork, they're going to look for that, right? Society is never going to make any progress until we all learn to pretend to like each other. So let's look at these, a to the 6th to the 6th power. Now, usually, generally speaking, when your exponent and your index are the same value, then your answer is simply just the variable to the first power. But once again, this is where WebWork is going to watch for those absolute value bars because the index here is even. A to the fifth raised to the index, the fifth root of a to the fifth is equal to a. And again, this can be negative, so this is not an absolute value. Odd numbered index, which means these absolute value bars are not necessary, so don't do that. A to the 23rd is equal to a to the 62nd root of that. 62 is an even number, so we get the absolute value of a. And the same thing is going to hold true for any kinds of variables here, right? As long as the exponent and index are the same, then we have our expression to the first power. And if that index is even, then absolute value bars are necessary. But if I were to change this up a little bit, say this was not the 18th power, but rather the 17th power, again, we do not need those absolute value bars, all right? So what about different variables? Different variables, you can take the square root of them by doing them separately. The square root of x to the second is equal to x. Square root of y to the fourth is equal to y squared, and that's all there is to it. Different variables and base numbers can be all treated separately. 100 divided by 2 is equal to 50, so the square root of x to the 100 is x to the 50th. Remember, 8 is not a perfect square as a base value, but as an exponent, it definitely is. Divided by 2 is equal to y to the fourth. And then on the denominator, the square root of 81 is equal to 9. So please, please don't confuse your base numbers and your exponents. Make sure that you are applying the correct rules for each. Can you have a fraction in an exponential value? 5 to the 1/2, x to the 3/4, 8 to the 1/3. The answer is yes, you can. So there is a direct translation between a fractional exponent and a radical, right? We have seen this before, which is the nth root of x to the b power. Take a look at where b is going. The numerator of this exponent is going right there. The denominator of this exponent is going over to the index. The numerator is going to the exponential value of the base in the radicand, and the denominator goes to the index. And this is a direct translation. And this can be written two different ways. Whichever way you write it is potentially advantageous for whatever numbers you are working with, right? And that means that inside your radicand is x to the b power, or inside your radicand is simply just x, and then you have parentheses with raising to the b power after that, right? So the b can go all the way out here with parentheses, and the n, the denominator, always goes to the index. So over here, we're going to end up with 5 as our base, raised to the first power, with an index of 2. And this is simply just the square root of 5. So whenever you see an exponent of 1/2, that indicates a square root, right? Once again, the first power exponent doesn't need to be written. The index of 2 doesn't need to be written, so we just have radical 5. But in the case where you do not have an exponent of 1/2, instead you have 3/4, then you do have to write those values down. And one thing I do want to caution you is that when you are writing some of these radicals, if I'm writing something like x to the 2 over 5 power, right? I'm going to translate this as the 5th root of x squared, not 5 radical x squared, right? So it's important that we write down this index. If it needs to be written down, you have to write it down, but it also has to be written correctly so it's not confused with a base value in front of a square root, okay? So make sure that you are writing these things clearly. So let's look at some fractional exponents and evaluate some things, right? So here we have negative radical 100, right? I told you guys way back in the beginning, an exponent modifies what? It modifies directly what is directly beneath it, right? Parentheses can change that, but the absence of parentheses means that this negative symbol is not being raised to the negative one, to the 1/2 power, right? So that translates to the square root, negative square root of 100, which is equal to negative 10. Now with parentheses there, such as negative 125 to the 1/3 power, this becomes the cube root of negative 125, again to the 1st power, but I'm not going to write that exponent of 1. And we saw before that this is equal to negative 5. And we also learned how to deal with negative exponents. Let's take care of that one first. So what is being flipped here? What is being modified by this negative exponent? What has to move its position? That's going to be negative 1 over 9 to the 1 over 2 power. Remember, we can flip and then ditch that negative sign. It does not affect this negative sign, again, because the parentheses are not there. So this is equal to negative 1 over radical 9, which is equal to negative 1 over 3. So what about this? Let's take this to another page, actually. Paste it. Because there's a couple ways to write this down. Remember those 2 ways I showed you how to write this down. One of them is we have the 5th root of 243 raised to the 2nd power. I'll call this number 1. Then we have the 5th root of 243, which is raised to the 2nd power outside. I'll call this scenario number 2. Now in scenario number 1, this requires us to multiply 243 times 243 and then take the 5th root of that value. Scenario 2 has us finding the 5th root of 243 first and then raising that number to the 2nd. So which one looks like it's easier? Right? I mean, 243 is a very large number, and taking the 5th root of that very large number seems quite difficult. So what if we took the 5th root of 243? It turns out it's actually 3 to the 5th power is equal to 243. So this will become 3 to the 2nd power, which is quite simple that we can calculate equal to 9. So again, sometimes it's advantageous to write it one way versus another. And in this case, it was advantageous to take the 5th root of 243 and then raise that to the 2nd power. So a negative exponent of 3 over 2 with parentheses on a fraction of 9 over 64. this is going to require some space as well. I'll copy this. I should have given myself more space to do some of these problems. But anyway, I have space here. So this is going to equal 9 to the negative 3 over 2, 64 to the negative 3 over 2. Now, since both of them have negatives, 64 to the 3 over 2 power and 9 to the 3 over 2 power. Since both of them were negatives, that means both of them get flipped. And now we can translate both of them as the square root of 64 to the third power over the square root of 9 to the third power. Now, once again, it might be easier to take the square root of 64 first and then raise that to the third power. And the same thing with 9. Let's take the square root of 9 and then raise that value to the third power, right? Instead of evaluating this first, let's evaluate this first. So we're going to have 8 to the third power over 9 to the third power. Right, and that's going to equal, oh wait, no, this should be 3 to the third power. Right, I forgot to take that square root. Sorry about that. 512 over 27. Now this one we should have space for. 36 to the raised to the 3 over 2, so that's the square root of 36 to the third power. Once again, we can take the square root of 36 first and then raise that to the third power. That's going to be 6 to the third power, which is equal to 216. Now, what if we had a negative 36 in here, right? In the parentheses here. Again, there's parentheses here, so that means that we're going to have the square root of negative 36 to the third power, or we're going to have the square root of negative 36, which is in turn raised to the third power, but either way you slice it, we got a negative number inside of an even index. This value is undefined. Now with the negatives gone, with the parentheses gone, let's take this straight to the value here. With the negatives gone, I miswrote that because this negative belongs outside here, just like that. Oh no, it doesn't even belong there. I flubbed that. It belongs all the way out here. Negative 6 to the third power is equal to negative 216. Right, remember, the only thing that's being modified here is that 36. So that's why the negative sits all the way out in front. So simplifying radicals. A radical number, such as radical 25, can simplify to a whole number of 5. Radical 36 can simplify to a whole number of 6. But what about something like radical 24? 24 is not a perfect square. Does that mean it can't be simplified? Well, the answer is no, it still can be simplified. There's two things that we want to know first about radical numbers. One is that you can multiply radical numbers and combine them into one single radical. Radical A times radical B is equal to radical AB. As an example, radical 2 times radical 5 is equal to radical 10. Now, does this hold true for addition and subtraction? The answer is absolutely not. It does not hold true. All right, if you were to subtract radical 2 minus radical 5 or something like that, you're not going to get radical negative 3 or something along those lines, or negative radical 3. It doesn't work that way, right? If the radicands are different values, then you cannot add or subtract them together. That's just what you're going to get, right? Think of x and y as two different variables, right? Algebra and the rule of like terms allows us to multiply x times y to get xy, but the rule of algebra does not allow us to add x plus y together in any capacity, so you just get x plus y, right? If you get 2x times 5y, then you can multiply 2 times 5 and write your variables together like so. But 2x plus 5y is not equal to anything other than 2x plus 5y plus or minus, right? So again, just like fractions, we see addition and subtraction being much more restrictive than multiplication and division also. So what is a simplified radical? A simplified radical means that your radicand does not have any factors that are perfect squares in it, right? Factors meaning two numbers that multiply to that number. The radicand can be a fraction, and you cannot have a radical value in the denominator, right? We'll talk about number 1 today, and we'll talk about 2 and 3 later. So here's how you simplify a radical. Let's look at radical 24. Now what I have written over here are all the factors of 24. That's 1 times 24, 2 times 12, 3 times 8, 4 times 6. Right? If there were any more factors, then we would write them, we would consider them. But as far as simplifying a radical goes, factors of 1 in itself are no good. That doesn't help. And in this case, the factors of 2 and 12 don't help. The factors of 3 and 8 don't help. Why? The factors of 4 and 6 do help. And the question is why? Why does this work and these don't? The answer is the presence of this right here, the radical 4. Radical 4 is a perfect square, which means that we can take the square root of 4 to be a whole number of 2. The other radical, radical 6, stays as radical 6. But what we're doing here is using this property of multiplication, kind of like backwards, right? Radical 24 can be written as the product of radical 4 times radical 6. Now, since radical 4 is a perfect square, we could take the square root of that, and now our radicand instead was 24, now it's 6, does not have any factors in it that are perfect squares. Let's take a look. Radical 50 is equal to 1 times 50. Radical 1 times radical 50, it's equal to radical 2 times radical 25, it's equal to radical 5 times radical 10. All of these are true, but really only one of them is helpful. So typically, I like to write the perfect square first and then the non-perfect square second, because we want to take the square root of that perfect square, in this case 5, and carry down the non-perfect square radical, and this is our answer, right? So when we are writing out our answers here, we're going to have a mixture of whole numbers and radicals. Write all of your whole number values first, whether they're variables or whether they're numbers, all of them should be written first, and then anything that's not a whole number, that's a radical number, a radical value, you can put that inside a single radical. We'll see that in a bit. So 32 is a slightly tricky one, right? Let's write out all the factors of 32 first. Again, I'm going to write out 1 and 32, even though I know it doesn't do anything. 2 and 16, 4 and 8. Is there anything else? I don't think there is. Now, what we see here is this doesn't work. This works and this works, right? 2 times 16 is 32. 16 is a perfect square. 4 times 8 is 32. And 4 is a perfect square. Which one is the correct one? Both of them are technically correct, but this is the better one. Why? Because the perfect square is larger. So here we get radical 16 times radical 2, which is equal to 4 radical 2. Now let's suppose that we used radical 4, radical 8. We're going to take the square root of 2 to get, sorry, square root of 4 to get 2. Now again, the rule that we are looking at is that there cannot be any factors that are perfect squares. Is there a factor of 8 that's a perfect square? This 2 stays on the outside, but since radical 4 times radical 2 is equal to 8, that means we can simplify this further. And we're going to get 2 on the outside times 2 from radical 4 times radical 2 for a total answer of 4 radical 2. So any whole numbers on the outside here are just going to get multiplied together. So same thing, same answer, just, one way was shorter and one way was longer, but both will yield a correct answer. So it's not that this is incorrect, it's just that it will take longer to simplify, that's all. So any numbers on the outside, oh, what happened? Any numbers on the outside are going to get carried through until there is another number, and then they're going to get multiplied together. So we're going to use 4 times 10 for 40. 8 times 5 is also equal to 40, but again, that doesn't help. So this is equal to 5 times 2 radical 10. And again, now these are going to get multiplied together, so we get an answer of 10 radical 10. Do a couple more examples here. Negative 2 radical 60. So just like before, right, again, here you can write out 1 and 60, 2 and 30. Let's use 4 and 15. Let's use 6 and 10. These are the factors, everything that multiplies to 60. I think I'm missing something. 3 times 20, right? There's a lot of factors of 60, but we have hit on one that contains a perfect square, so let's go with that one. Negative 2 on the outside, square root of 4, square root of 15 is going to equal negative 2 times 2 radical 15. Multiply those outside values, negative 4 radical 15. And here, since there are so many factors of 60, let's just take a look at this for a minute. Are there any factors of 15 that are perfect squares? Again, discounting 1 and itself, we're good. Right? Technically 1 is a perfect square, but it's not going to help you simplify. So what happens if we have a mixture of numbers and variables? Just like with fractions, we're going to treat them separately, right? 2 and 24, 4 and 12, 3 and 16, 8 and 6. These are all factors of 48, but I'm going to circle this one because it has the largest perfect square. Remember, this one also is a perfect square, but this one's bigger, so let's go with that one. So we're going to get the square root of 16 times the square root of 3 times the square root of x to the 28th power, right? Let's take them all separately. And I'm going to underline 16. I'm going to underline x to the 28th. Why? Because both of them are perfect squares. Remember the rule of exponents? Since that is an even number, that means it's a perfect square. We can take the square root of x to the 28th by dividing 28 divided by 2. So we get 4x to the 14th radical 3. Right? The 4 comes from the square root of 16. X to the 14th comes from the square root of x to the 28th. So let's take this a little bit further out. Square root of 24, we can use 4 and 6. X to the 22nd power. And then y to the 100th power. All of these are perfect squares. So let's underline our perfect squares. We'll take the square root of those first, 2, x to the 11th, y to the 50th power, and then whatever is not a perfect square, such as this, it'll get written down at the end. 2x to the 11th, y to the 50th, radical 6. Now let's begs the question, what happens if your variables have an odd numbered exponent, such as here, x to the 23rd power? Now remember, the rule of exponents, when you are multiplying common bases, x to the 10th times x to the 13th adds up to be x to the 23rd. So that means using this rule of multiplication and addition of exponents, we can separate x to the 23rd into radical x to the 10th and radical x to the 13th. And guess what? This is a perfect square. So x to the 5th, radical x to the 13th. Now, is it possible to split up x to the 13th into factors such as, let's say, x to the 8th and x to the 5th? The answer is yes, because this is going to equal x to the 13th. So now we can split this up again. We have x to the 5th out here, and then x to the 8th inside a radical, x to the 5th inside a radical, because again, it's got to add up to 13, and 8 plus 5 does that. Is this a perfect square? Yes, it is. So we get x to the 5th, x to the 4th, radical x to the 5th. And that's going to equal x to the 9th times radical x to the 5th. Right, because we added 5 plus 4 to get 9. So can we split up x to the 5th over here? And the answer is yes. X to the 4th times x to the 1st is going to equal x to the 5th. So let's go with x to the 9th, radical x to the 5th, radical x. Again, we have a perfect square right there. So that's going to equal x to the 9th, x to the... Oh, wait. No, I wrote that wrong. That should be 4. X to the 2nd, radical x. And that's going to equal x to the 11th power, radical x. And can we split this up? Can we write out any factors? No, because it's x to the 1st power, so it's just 1 times x to the 1st power. So is an odd-numbered exponent significantly longer than an even-numbered exponent? Well, depends on how you look at it, because let's go all the way back to the beginning. I wrote down 10 and 13, but why? Why did I write down 10 and 13? Could I have written down something else, maybe x to the 18th and x to the 5th? Could I have written down x to the 20th and x to the 3rd? Could I have used x to the 22nd power and x to the 1st power? The answer is yes. There is no rule dictating which combination of numbers you have to use to add up to your original odd number. So let's use x to the 21st and 22nd and x to the 1st. This is a perfect square because it's even, divided by 2x to the 11th power, radical x, and guess what? We are done. So is it significantly longer to simplify an odd-numbered exponent? Not really. Not as long as you are choosing the correct values, then no, it's not significantly longer. And the correct value is always going to be an exponent of 1. Always. Right? Because we are taking square roots here. That means that if we look at this, we look at radical 20 as radical 4, radical 5. But if we look at this x to the 7th power as always x to the 1st and then x to the 7 minus 1, x to the n minus 1, if n is an odd number, then we are always going to get an even number here, which means that it will be a perfect square. So let's take the square root of those things first. 2x to the 3rd power. We took the square root, so it comes outside the radical. Now what's left in the radical? I will underline that in pink over here. These are, now we have two separate values that are not perfect squares. So they're going to get combined into a single radical. Do not separate them, keep them together. I don't know why I numbered this one. Anyway, so let's look here. Radical 32, we did that already. We used 16 and 2. Now we have x to the 12th power, and we have y to the 1st and y to the 18th, again from 18 minus 1. So I have a question here. We separated this y's into two values, y to the 1st, y to the 18th. We did not do that for x. And what's the reason for that? Because x to the 12th is a perfect square. You only need to do this adjustment for an odd number. If the exponent is an odd number. If the exponent is even, you do not need to do that. It's a perfect square. Do not fix it. Just take the square root. 4 x to the 6th, y to the 9th, radical 2y. Right, so just to show you, we get 4 from square root of 16. We get x to the 6th from x to the 12th. We get y to the 9th from radical y to the 18th. And everything that we didn't take the square root of stays. So this will be the last one. Let's do this in purple just because we have the square root of 125. So what multiplies to 125? That's going to be 25 times 5. We're going to have a to the 21st, which means we're going to have two a's. One of them is going to be 1 as always. The other, 21 minus 1, is 20. 31 is an odd number. So we're going to have b listed twice, 1st and 30th. We're going to have c listed twice because that's an odd number. C to the 1st and c to the 8th. I ran out of space, so let's move this over so I can write down d to the 16th power. Now, once again, we have two a's, two b's, two c's here. We split them because they were odd numbers in the exponents, but we did not split d to the 16th because it is already a perfect square. So let's underline 25, a to the 20th, b to the 30th, c to the 8th, d to the 16th. These are our perfect squares, and I'll put a double underline in front of the non-perfect squares. So let's take the square root first of the perfect squares. That's going to be 5, a to the 10th, b to the 15th, c to the 4th. Right, so that's 1, 2, 3, 4 perfect squares. We missed the d. So again, remember 16 is a perfect square as an exponent because it is even. So divided by 2, that square root of d to the 16th is not equal to d to the 4th. So that's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So what's left is 5a, b, c inside of our radical. That's 1, 2, 3, 4 pieces inside of our radical. And there it is. Just make sure that you're keeping track of all the different letters and numbers and things of that nature, and you'll be just fine. Thank you for watching.